Hey guys, this is Mrs. Butcher. This video is about graphing general rational functions, which means we're taking the simple ones we did a couple days ago and taking it to a higher level. So here we go. Okay, when we graph general rational functions, there's 6 main rules that I want you guys to memorize, and these are explained more in detail on the handout that I've given you. But those rules apply to vertical asymptotes, which we've talked about, horizontal asymptote, there's only going to be one, but vertical there could be more than one. X-intercepts and Y-intercept. You can have more than one X-intercept, but you can only cross the Y-axis one time if it crosses it at all. You might have a slant asymptote. Those are kind of tricky, but we'll get there. And holes. You could have a hole in your graph. Alright, vertical asymptotes occur because you cannot divide by 0. And we saw this in our simple rational functions. All you have to do, no matter what your rational function looks like, is set the denominator of the fraction equal to 0 and solve for x, because that will give you the x values that you can't use, and so those will be the equations of your vertical asymptotes. And I have an S on asymptote because you can have more than one. Okay, the horizontal asymptote, and there is only going to be one if there's going to be any at all. We've talked about that too. If the numerator and the denominator are the same degree, like we did a couple days ago, you're going to take the ratio of the leading coefficients. So if I had something like 3x to the 5th plus 7x plus 2, whatever, over 5x to the 5th minus 1, whatever, you're looking at the degree, and if it is the same, no matter what it is, then you take the ratio. So your horizontal asymptote is always a y equals, because it's a horizontal line, and then in this case it would be 3 over 5, and we have talked about that before. But there are 2 other special cases. We could have a bigger degree on top, and we could have a bigger degree on bottom, and each of those have their own sets of rules. Alright, so if your numerator is smaller than your denominator, if it's big on bottom, that's what we did when we did the first ones, like 1 over x. That's bigger on the bottom. It's got a higher degree on the bottom. I want you to think of a famous celebrity who is just a little bit big on bottom. Alright, see, this is J-Lo. And J-Lo is big on bottom. And so if your fraction is big on bottom, then J-Lo rhymes with 0. And I want you to think, big on bottom, J-Lo 0, y equals 0 is where your horizontal asymptote goes, every time. Okay, and then the third situation you could have is if your numerator has a higher degree or a higher power than your denominator, so if it's bigger on top. So I want you to think of a celebrity who's big on top, and you have to think back to Miss Butcher's childhood here. Think of about a old country singer who's famous for being big on top. Okay, see, this is Dolly Parton. You've seen her in some movies. She's big on top. I mean, look how big that hair is. My goodness. But you can't see it in this picture. I'm just going to have to tell you, and you'll have to take my word for it, that Dolly Parton has no asymptote. I'm sorry about the handwriting. I can't find my stylus, so I'm writing with my finger. But anyway, yeah, so if it's bigger on top, think Dolly Parton and think none. No asymptote at all. No horizontal asymptote, I should say. Okay. Alright, the third thing is the x-intercepts, and yes, you can have more than one. So if you recall, when you draw a graph, and then it crosses the x-axis, whatever that looks like, that's where y equals 0. So if you took your fraction and set it equal to 0, the only way that it would equal 0 is if the numerator was 0. 0 divided by anything is 0. Remember, the bottom can't be 0. We've already talked about that. So all you have to do is take the numerator and set it equal to 0, and then you'll know your x-intercepts. Yeah, I'll take that. Looks better. Set numerator equal to 0 and solve for x, and those are your x-intercepts. Alright, there's only going to be one y-intercept, and so once again, if you think of the graph, the y-intercept is where x equals 0. So to find the y-intercept, you just plug a 0 in everywhere you see an x and solve for y. Plug a 0 in everywhere you see x, solve for y. That'll tell you your y-intercept. Alright, the fifth thing is the slant asymptote. That happens only when The degree of the numerator is 1 power higher than the degree of the denominator. And the way to find your slant asymptote is kind of tricky, but that's why we spent a day doing our long division. You are going to just take the fraction and you're going to do polynomial long division, and because the degree of the numerator will be 1 more than the degree of the denominator, you'll always end up with a linear solution, and that linear solution will be your asymptote. If you end up with a remainder, you just ignore the remainder. All you have to do is get the linear part of it. You can stop. You don't have to find the remainder, and we'll practice that in a little bit. Alright, and then the 6th rule is about the holes. A hole is an infinite point in the graph where if you were to factor the top and the bottom and have a factor cancel out, you might have a hole. And I know y'all hate factoring, but you really need to remember how. It's still very important. So we're going to factor, and then if any of your factors cross out, you're going to graph your function all based on the simplified version, except you're going to take the part that you crossed out and you're going to set it equal to 0 to figure out the x value of your hole. And then you'll take that x value and you'll plug it in to your simplified fraction to get the y value of your hole. And once again, we will practice that in a little bit. Alright, and then the rest of the graph, you can just make a table. You will have your calculator, so you'll be able to get a good idea of what the rest of that graph is going to look like, and then you can just look at the table in the calculator and plot points off of that. Alright, so we're going to do a few examples. Hang on just a second. In this example, we're going to graph y equals 3 over x squared plus 2. And I'm just going to go through all my pieces in order. It doesn't really, you don't have to go in order, but okay, the first thing we're going to do, the vertical asymptote. That's when you set your denominator equal to 0. If I set x squared plus 2 equal to 0, I'm going to get x squared equals negative 2, which we know is not going to give us real answers. And that can happen. That just means you won't have any vertical asymptotes. So for VA, for vertical asymptote, we're going to put none. Alright, second thing, horizontal asymptote. Horizontal asymptote, you have to look at the degree. Is it big on top, bottom, or the same? This one's big on bottom. Big on bottom is J-lo, which rhymes with 0, so y equals 0. And make sure that you dash that horizontal asymptote into your graph. Third thing, x-intercepts. When it crosses the x-axis, y is 0. So if I set my numerator equal to 0 here, I wouldn't get any x values. And if that happens, that's okay. We don't have any x-intercepts. There's none. Fourth thing, y-intercepts. To find your y-intercepts, you plug a 0 in for x. So if I had 3 divided by 0 squared plus 2, I would get 3 halves. So when x is 0, y is 3 halves. Sorry about the printer in the background there. But 0, 3 halves. So I'm going to put that on the graph. 0 and 1.5 is here. Okay, the fifth thing was holes, and remember to have slant asymptotes, and to have a slant asymptote, your degree on top has to be 1 higher than the bottom. Here our degree on top is 0, our degree on bottom is 2. That's not the case, so we have no slant asymptote. And then the last thing is the holes, and we didn't have any factors that crossed out, so we don't have any holes either. So now the last thing we need to do is just make a table and plot points on this graph. So if I make a table for x and y, I already know 1 point, so if I plugged in a 1 for x, I'd have 3 over 1 squared plus 2. 3 over 1 plus 2, 3 over 3 is 1. If I had x is 2, I'd have 3 over 2 squared plus 2. So that's 4 plus 2 is 6, 3 over 6 is 1 half. If x was 3, I'd have 3 over 9 plus 2. So that would be 3/11ths. And it's getting smaller and smaller, and it's going to approach that asymptote. In the other direction, if x is negative 1, 3 divided by negative 1 squared plus 2 is the same thing as positive 1 squared plus 2, because when you square a negative, you get a positive. So negative 1, 1. Same thing with the negative 2. I'm going to get the same thing as when I had a positive 2. So negative 2, 1 half. And negative 3 squared is still 9 plus 2 is 11, so negative 3 gives us 3/11ths. So if I plot those, 1, 1, 2, 1 half, 3, 3/11ths, negative 1, 1, negative 2, 1 half, and negative 3 3/11ths. And I know it's going to approach the asymptotes just like this. It looks like a little anthill. Only it goes on forever in both directions. And that is it. Here's another example. We have y equals x squared minus 9 over x squared minus 4. These are factorable. So the very first thing you always want to do is factor. So that's x plus 3x minus 3. And on the bottom we have x plus 2x minus 2. And then once you've factored, at this point you would look and see, can I cancel out any of the factors? And no, we cannot. So when we get down to the wholes question, we'll say no wholes. Alright, so if I wanted the vertical asymptotes, I'm going to set the denominator equal to 0. And I actually have two parts to my denominator, so I have two vertical asymptotes. One at x equals negative 2, and one at x equals positive 2. So write them both down and dash them both into the graph. For horizontal asymptote, we're going to look at the degree of the top and the bottom. This time they are the same degree, so we're going to do the ratio of the leading coefficients, which is 1 to 1. So we're going to have a horizontal asymptote at y equals 1. Dash that into your graph as well. Xintercepts are when the numerator is 0. So if I set each of these equal to 0, I'd have two Xintercepts. One of those is going to be at negative 3, 0, and the other one will be at positive 3, 0. So plot those on the graph. To find your y-intercepts, you plug in, or y-intercept, you plug in a 0 for x. So if I had 0 squared minus 9 over 0 squared minus 4, I would have negative 9 over negative 4, which is 9/4. So my y-intercept is at 0, 9/4. 9/4 is 2 1/4, so right there. All right, slant asymptote. Degree on the top has to be 1 higher than the bottom. Sorry about that. Which we do not have, so no slant asymptotes. And holes, we already said. We didn't cross any factors out, so no holes. All right, so now that you look at this graph, you see these dotted lines on here. This divides it into different portions, different branches. We're going to have 3 different branches. And then if you just looked at the points, you would think it might look something like the first one we did, but it's not going to look anything like that. So now we have to make a table. When you don't have a calculator, that's what you have to do, make a table of values to plot. And I'll just start over here in the middle section. I already know the 0 point, so when x is 1, if I have 1 squared minus 9 over 1 squared minus 4, 1 squared is 1 minus 9 is negative 8, 1 squared minus 4 is negative 3, so I have a point at 8/3, which is 2 1/3. 2 1/3 right there. All right. If x was negative 1, I would have the exact same thing, right? Because these are both squared, so it would still be the same thing. So it's going to be here. And since it's going up, I can plug in 1 1/2 to be sure, but it's not going to come back down because it's not going to cross this this asymptote here, so it's not going to come back down. It is going to go up, and we know it has to approach this asymptote here. Same thing on this side. It's not going to come down, so we know it's going to approach that asymptote there. So I can sketch in. That's enough points for me to sketch in this middle part. It looks kind of like a little parabola on the inside. All right, now over here on the right, over here, we got the x is 3, so let's plug in x is 4. 4 squared is 16 minus 9 is 7. 4 squared is 16 minus 4 is 12, so 7/12. It's just a teensy-weensy bit more than a half, so right there. And you can tell what this is going to do. It's going to approach this asymptote. It isn't going to cross it. There's the bell again, sorry. And on this side, it's going to be going down and approaching that asymptote. On the left here, if I plugged in a negative 4, because they're both squared, I'm going to get the exact same thing. I'm going to get it 7/12. So it goes a little bit more than a half right here. And this side will look exactly like the other side. And so there is your graph with your 3 branches. All right, example 3 says y equals x squared minus 2x minus 3 all over x plus 2. And you want to factor the top if you can here. X squared minus 2x minus 3 would give you x minus 3 and x plus 1. And that's all over x plus 2. So nothing cancels out. This is our function. You can put it in your calculator to graph it. First thing we want to locate are vertical asymptotes by setting the denominator equal to 0. So that means x equals -2. If x was -2, we would be dividing by 0. Only one vertical asymptote for this graph. Write your horizontal asymptote. This one is big on top. Remember, big on top is Dolly Parton, and she has no asymptote. So no horizontal asymptote here. All right, x-intercept. Set the numerator equal to 0, and if we do that, we're going to get 3, and we're also going to get -1. So we have two x-intercepts, at -1, 0, and +3, 0. Okay, y-intercept, plug in a 0 for x. That would give us 0 squared minus 2 times 0 minus 3 over 0 plus 2, so -3/2. -1.5 right there. Slant, that happens when your top is 1 degree higher than the bottom. Well, that means that we need to do some long division. All right, and I didn't leave room for that, so we're going to do it on the next page. But before I do that, let's finish this up. Holes, we didn't cancel anything out, so none. All right, now I'm going to turn the page so that we can do our long division to find our slant asymptote. Remember, we're going to take this original problem and we're just going to set it up like we did the other day. So set up your long division with the numerator in the inside of the little house, the denominator on the outside, and then remember we're going to just look at x and x squared. X goes into x squared x times. So we put an x up here and we multiply. X times x is x squared. X times 2 is plus 2x. Then you put parentheses around it, subtract. X squared minus x squared is nothing. -2x minus 2x is -4x. Bring down your -3. X goes into -4x -4 times. And I can stop because there's my linear equation right there. I don't need a remainder. I don't care about the rest of it. The slant asymptote is going to be at y equals x minus 4. Okay, so our slant asymptote we determined was at y equals x minus 4. That's just a line with a y-intercept of -4 and a slope of +1. So I'm going to dash in my my diagonal slant asymptote. And then the rest of the points we can get by looking at the calculator. Now be careful because if you just graph it on a 10 by 10 window, you're only going to see, sorry about that, this top branch of the hyperbola. But you do have a bottom branch too. You'll have to change your window a little bit and look, or just look at the table. But we have points, -3, -12, down here, and -4, -10.5 here, -3, -12 there. So we know it's going, -7, -12. So there, not there. So it mirrors the other side like that. Now the domain and the range of this is kind of tough, so I'm not going to make you do it, but domain would be -infinity to -2, -2 to infinity. Range would be -infinity to the top of this hump, and then the bottom of this part up to infinity. All right, this is the last example. We've got y equals 2x cubed plus x squared all over 2x plus 1. And once again, the very first thing you always want to do is factor, just to make sure things will or won't cancel out. So here on the top, I can factor out a greatest common factor of x squared, and then I have 2x plus 1 left. And on the bottom, we have 2x plus 1, which doesn't factor. But these two groups match, so you can cross them out. And that means that all we really have is y equals x squared. And that's a very easy graph to do. It's a parabola. However, because we crossed out a factor, it's going to be a parabola that has a hole in it. So everything that we do for this graph is going to be based on only y equals x squared, except the hole. Vertical asymptote, parabolas don't have asymptotes, none. Horizontal asymptote, none. X-intercept. If I set x squared equal to 0, x equals 0, so 0, 0. Y-intercept. If I plug in a 0 for x, y is 0, which makes sense because 0, 0 is an x and y-intercept at the same time. A slant asymptote, we don't have any. We don't even have a denominator after we cross everything out that cancels, so no slant asymptote. So that leaves us with the wholes, or in this case, whole. There's only one. To find the whole, you take what you crossed out, 2x plus 1, and set it equal to 0. So that means we have 2x equals negative 1, x equals negative 1/2. That is the x coordinate of your whole. But a whole is a point, and you need a y coordinate. So to find the y coordinate, you take this x value and plug it in to the remaining equation. So if I said y equals negative 1/2 squared, I'd get positive 1/4. So your whole is at negative 1/2, positive 1/4. It's a point. And you're going to mark that on the graph with an open circle. So at negative 1/2, well here, let me draw some axes. And at negative 1/2, 1/4, I'm just going to be a little bitty right here. I'm going to draw an open circle. And then we know our x and y intercepts is 0, 0. And we know this is y equals x squared. It's a parabola, 1, 1, 2, 4, 3, 9, and so on. So all the rest of it just gets sketched like a normal y equals x squared. The only difference is it has that open circle on there because it has a hole. So remember, to find the whole, you first take what you've crossed out, set it equal to 0, get x. Plug that x in to the remaining equation and get y, and that's the ordered pair of your whole. Okay, for this graph we need a domain and range. So the domain is all real numbers except for the whole. So all real numbers except negative 1/2. So I'm going to say negative infinity to negative 1/2, and then negative 1/2 to infinity. So when you're doing domain and range, you write it just like you would with an asymptote. So our range, this one starts at 0, hard bracket because it touches 0, stops at the whole, which is at y is 1/4, picks up again after the whole, 1/4, and then goes on infinitely to infinity. And that is the lesson for today. I know it was long, and I'm sorry, but this is one of our harder lessons. So you guys have a good night, and I'll see you tomorrow.